This infinite sum is called the Riemann Zeta function. This function is famous for several reasons. It's intimately connected to the prime numbers, it's the topic of one of the biggest unsolved problems today, and its value at -1 is responsible for the bizarre claim that the sum of all the natural numbers is -1/12. But there's one problem. The sum only converges when the real part of S is greater than 1, and a lot of the interesting stuff happens elsewhere. Well, the topic of my last video was not infinite sums, but fractional sums. That is, we saw how to extend summation to allow for fractional, irrational, and even complex upper bounds. In this video, we'll see that there's a surprising connection between these fractional sums and the zeta function. This connection will give us an explicit way to extend the zeta function to the rest of the complex plane, and it'll fully explain the function's behavior at the negative integers. For this video, I'll assume that you're comfortable with some calculus, limits, derivatives, and infinite sums. You should also be familiar with complex numbers and how they're represented as points on the complex plane. Finally, I'll be using the formula for fractional summation that I derived in my last video. I understand that this formula is as bulky as it is obscure, and that it would be quite a time commitment to watch the full video about it. So I'll spend a couple minutes in this video summarizing why it works, and you won't need to watch the other video unless you really want a deeper understanding of it. Now, all the functions in this video will have complex numbers as both their inputs and their outputs. We usually use the letter z to represent a complex number, but for the zeta function, the convention is to use s. So don't worry when I switch the letter of the variable. There's no deeper meaning behind it. So, let's get started. We're all used to graphing real functions in 2 dimensions, with the input on the x-axis and the output on the y-axis. But for complex numbers, we need both a real dimension and an imaginary dimension for both the input and the output. The combined 4 dimensions just don't fit in our universe. So instead of using space to represent the function, we'll use color. This method is called domain coloring. We'll start by assigning a unique color to every point on the complex plane. We determine the hue of the color by the angle of the point relative to the origin, and the lightness of the color depends on the distance from the origin. So it fades to black at 0, and if I zoom out, you can see that it fades to white away from the origin. This will be our standard color scheme for the complex plane, and we'll use it for the output of the function. Let's pull up another copy of the complex plane for the input, and let's choose this function as an example. On the left, I'll place a point, say z, and on the right, I'll show where the function maps this point, f of z. If I move the input point, the output point reacts as dictated by the function. To get our domain coloring, we color each point based on where the function maps it. For instance, right now f of z is this reddish color, so we paint z the same color on the input graph. And if we move z over here, it maps to green, so we'll color this point green. The idea is to do this for every single point on the plane. Okay, maybe scribbling is a silly way to see it happen, but at the end, we'll have a full picture that uniquely corresponds to this function. I'll also add the warped grid lines to the picture, because this gives our eyes some more visual structure to latch onto. And it looks cool. This domain coloring lets us see some properties of the function at a glance. In particular, the function has zeros wherever the hues kind of coalesce and it fades to black. Poles, that is, isolated points where the function shoots to infinity, are similar, only they fade to white. This isn't too important for this video, but it's just good to know what you're looking at. Let's quickly take a look at some familiar functions. Here's the identity function. Pretty boring. Here's z squared. A little more interesting. And here's 1 over z. This is what sine looks like. And here's the exponential function. So let's look at the Riemann Zeta function, the infinite sum of 1 over k to the s. Well, this isn't an infinite sum right now, but I'll let the number of terms increase toward infinity so we can watch it converge. As you can see, it converges when the real part of s is greater than 1, but it blows up everywhere else. For instance, if we plug in -1, the sum simplifies to the sum of k. This is just 1 plus 2 plus 3 and so on, which obviously diverges. And yet it's said that zeta of -1 is -1/12. So what's going on here? Well, I actually haven't given you the full definition of the zeta function. It's not just defined as this sum. It's defined as the analytic continuation of this sum. Okay, what does that mean? Well, an analytic continuation of a function is a complex differentiable extension of that function to a larger domain. Let's see an example. Consider the sum of z to the k. When we increase the upper bound toward infinity, we can see that it converges, but only in the unit disk. Thus, this infinite sum defines a function on the unit disk. Now, you may recognize this as a geometric series, in which case you'll know that it converges to 1 over 1 minus z. But 1 over 1 minus z isn't restricted to that disk. It defines a function on the whole complex plane. Well, except at z equals 1 where there's a pole. Since this function is differentiable on this domain, it is the analytic continuation of the function defined by the infinite sum on the unit disk. Notice that I said the analytic continuation, rather than an analytic continuation. This is because complex differentiability is a surprisingly rigid constraint. So rigid, in fact, that there can only ever be one analytic continuation of a function to a given domain. I know that seems too good to be true, but it genuinely is a proven theorem. Analytic continuation is unique. So if I talk about the analytic continuation of this infinite sum, I can't be referring to anything other than the function defined by 1 over 1 minus z. The situation is the same with the zeta function. We have a formula which defines a function only in a certain region, and there can be only one analytic continuation of it to the rest of the plane. Therefore, it's completely unambiguous to define the zeta function as this analytic continuation. That is, if such an analytic continuation exists. But, of course, we haven't yet demonstrated that it exists, and much less do we have a formula for it. But we will by the end of this video. However, we won't get there by diving deeper into the zeta function. In fact, everything up until now has just been the background for this video, and we should try to let it rest in the back of our minds as we point our curiosity towards a totally different topic: fractional sums. The sum of a function from 1 to z usually only makes sense if z is a positive integer. But in my last video, I showed how this crazy expression extends the definition of summation to allow z to be any complex number. As I said earlier, I can't give a full derivation in this video, but I'll give a quick explanation of why it works. This formula has two parts. The first part contains the core of the idea, but it only works for a small class of functions. That's why the second part is necessary. It's a correction term that vastly expands the collection of functions that the formula works for. But let's just focus on the first sum right now. For the sake of example, I'll let z equal 3. Now, the reason this formula works is that it's a textbook example of a telescoping sum. Let's write out all the terms of the sum explicitly. If we shift all the subtractions down 3 spaces, we can see that most of the terms are now plus something minus that same thing. So they cancel out, and like a telescope, the whole thing collapses to just the first 3 positive terms and the last 3 negative terms. We can express both of these as summations. Now, all the 3's in this formula are only there because we set z to be 3, but this will work for any positive integer z. Now, by rearranging things, we end up with an unnecessarily complicated expression for the sum of f from 1 to z. This works for any choice of n, so we can take the limit as n goes to infinity. Now, if the function f approaches 0 as its argument increases, this sum here will approach 0, so it disappears in the limit. And with that sum gone, the left side becomes valid for any complex number z, so we've successfully extended the sum. But what if f doesn't approach 0? Then we can't ignore that sum, which is a problem because it has z in its upper bound. That's why the actual formula has this correction term. This term is an interpolating polynomial that becomes arbitrarily close to this leftover sum as n increases. So in the limit, it matches it perfectly, and we can swap it in. And that's the gist of the formula for fractional sums. Now, in case you're not familiar, this delta here is the k-1st forward difference with respect to n. The forward difference is a discrete version of the derivative. It's simply defined as the difference between two consecutive values of the function. The order of the forward difference is the number of times we repeat this operation. So the 0th order does nothing, the first order applies the forward difference once, the second twice, and so on. Don't worry too much about forward differences. This here is a binomial coefficient, z choose k. These are usually defined in terms of factorials, which seems like a problem because you can't take the factorial of a non-integer number. Or can you? But we don't need to. We can expand z factorial to z times z minus 1 times z minus 2 down to z minus k factorial. And that cancels with the z minus k factorial in the denominator. Now, when expressed like this, the binomial coefficient only requires k to be an integer, which it is, so there's no problem. I've got one final note here, and this one will be important. There's a free parameter, m, on top of the sum. This is the order of the correction term. The greater it is, the more functions this formula will work for, but the more work it'll be to compute it. The first case we saw, where there was no correction term, is really the case where m equals 0. Remember, that only worked when the function approached 0. The general rule is that the function has to grow strictly slower than z to the m. For this video, we'll only be taking the fractional sum of one specific type of function, z to the p, where p is a complex number. The growth rate of z to the p is determined by the real part of p, so this formula works only when the real part of p is less than m. This isn't a problem because we can always choose m to be big enough, but it'll be important later. Alright, I've done more than enough talking about fractional sums, so let's visualize them. In addition to the domain coloring, I'm plotting p as a point on the complex plane. Right now it's 0, and since anything to the 0 is 1, the sum is just 1 plus 1 plus 1 z times, which obviously just gives us z. That's about as boring as it gets, so let's change p. With p set to 1, the sum becomes 1 plus 2 plus 3 up to z. You may have heard before that this is z times z plus 1 over 2, and indeed, that's what our fractional sum formula is giving us. My personal favorite value for p is -1. If you've been with me from the beginning, this is the extension of the harmonic numbers from my first video. But we don't need to stick to just real numbers. We can move p anywhere on the complex plane, revealing a whole world of beautiful functions. I love how no matter what we choose for p, the function is always perfectly smooth. Well, it's discontinuous on the negative real axis where there's a branch cut, but everywhere else it's differentiable. So we can ask a question that normally doesn't make any sense. What is the derivative of this sum? To find out, we need to take the derivative of the whole fractional sum expression. Well, let's make things easy on ourselves and set m to be 0. This means we drop the correction term. And then we can save some space with the infinite sum shorthand. Just remember, with m being 0, it only works when the real part of p is less than 0. So, putting aside concerns about interchanging limits for now, we can distribute the derivative inside the sum. This first term is a constant, so its derivative is 0, and the remaining derivative is just a simple case of the power rule. Now we can take this factor of -p outside the sum, and voila, we have a nice formula for the derivative of this sum. Hang on a second, this feels kind of familiar. What happens when z is 0? We just end up with -p times the infinite sum of k to the p minus 1. which can also be written as 1 over k to the 1 minus p. This is the Riemann Zeta function of 1 minus p. That's crazy, right? We take the derivative of this fractional sum, and the zeta function just kind of falls out. We can do something cool with this. We can use it as a new definition for the zeta function. Let's flip this around and isolate the zeta. We can define s to be 1 minus p, which also means that p is 1 minus s, so we can substitute that in for p. And now we have an alternative definition of the zeta function. Zeta of s is 1 over s minus 1 times the derivative of this fractional sum evaluated at 0. Now remember, we started by supposing that the real part of p was less than 0. Well, p is just 1 minus s, so the real part of 1 minus s is less than 0. After some rearranging, this is the same as saying that the real part of s is greater than 1, which is the restriction that the zeta function already had. But this is no longer an intrinsic limitation of the zeta function's definition. Rather, it's a result of us using the simplest version of the fractional sum formula, the one with no correction term. Or, in other words, because we set m to be 0. That's the only reason why the real part of 1 minus s has to be less than 0. Really, it just has to be less than whatever we set m to be. This translates to the real part of s being greater than 1 minus m. Therefore, if we choose larger m, this new definition of zeta should be able to handle more values of s. To test this idea, let's keep it simple and let m be 1. This should work if the real part of s is positive. Now, this sum just has one term, with k being 1, which is pretty nice. Z choose 1 is just z, and the 0th order forward difference does nothing. So this is what we have to take the derivative of. As before, we'll distribute the derivative inside the limit. In the last term, since the derivative of z is 1, we're just left with n to the 1 minus s. The rest goes exactly as it did before. This term disappears, and we use the power rule for this one. Now we can plug in 0 for z, and we can distribute the 1 over s minus 1. This fraction is just 1, so it disappears, and as a final step, I'll write k to the negative s as 1 over k to the s. And that's it. Let's see if this works. Beautiful. We really have an analytic continuation of the zeta function. Not to the whole complex plane, but we have an additional strip that we didn't before. This is actually called the critical strip because all the non-trivial zeros of the function live in it. Here's the first one. Don't worry if you don't know what that means, it's not important for this video. Now, we gained this strip by setting m to 1, and if we set m to 2, we'll gain an additional strip, and likewise for 3, 4, 5, and so on. So by choosing m as large as we want, we can compute the zeta function on the whole complex plane. Of course, you can't put this into a calculator because the calculator won't know what to do with the derivative of a sum. So let's turn this into a formula that only uses standard operations by plugging in the definition of the fractional sum. I'll distribute the 1 over s minus 1 and the derivative to both lines here. We already did this first line twice, and we saw that it's just the sum of 1 over k to the s. For the other part, the binomial coefficient is the only thing that contains z, so that's the only thing we need to take the derivative of. But we don't differentiate binomial coefficients every day, so let's walk through it. Remember, z choose k is defined as this product, so we just need to take the derivative of this. Let's separate the first z from everything else. By the product rule, we have the derivative of z times everything else, plus z times the derivative of everything else. The derivative of z is just 1, which does nothing, and the derivative of everything else doesn't matter. Remember, we only care about the derivative when z equals 0, and when we substitute that in, we can see that we're multiplying this derivative by 0, so it disappears. Now, the numerator is just -1 times -2 up to negative k minus 1. This is -1 to the k minus 1 times k minus 1 factorial. That k minus 1 factorial mostly cancels with the k factorial, so we're just left with k in the denominator. And that's it. So we can plug this in for the derivative of the binomial coefficient, and after a little cleanup, we have a formula for the analytic continuation of the zeta function. Now, I have to come clean. This is not a very good way to compute the function. In fact, when I used it to make the animations for this video, it didn't even work. It turns out 32-bit floats just don't have enough precision, and even if they did, it converges super slowly. But I promise, theoretically, this is sound. I know I've been playing it loose in this video. I never proved that this function is differentiable, which is the requirement for it to be an analytic continuation. I also never justified the interchange of the limit and the derivative in the derivation. In fact, I never even showed that the fractional sum formula converges, which is the backbone of this whole video. Now, everything is valid, but you need some more background knowledge to prove it, and that wouldn't really fit in this video. So instead, I wrote a proof on my site, and you can find that linked in the description if you're interested. Now, this connection with fractional sums may not give us the most practical formula for computing the zeta function, but it does offer a really nice explanation of the function's value at the negative integers. If s is 0, the fractional sum simplifies to the sum of k to the 1. When s is negative 1, we get the sum of k squared. Negative 2 gives us k cubed, and so on. These cases, where the exponent is a natural number, are much simpler than general complex exponents because they have closed-form solutions. Some of the low-order cases have been known for millennia, and in the mid-17th century, Blaise Pascal discovered a general method to solve every natural number power. He showed that these sums are polynomials of one higher degree than the power in the sum. And thanks to these polynomials, we can easily evaluate zeta at any negative integer. Clearly, the derivative of a polynomial evaluated at 0 is just the coefficient of z, the linear coefficient. So to find zeta of negative 1, for example, we just observe that we need the derivative of the sum of k squared. That sum is a polynomial whose linear coefficient is 1/6. So, by substituting that in and simplifying, we can see that zeta of negative 1 is negative 1/12. Now, Pascal's method of solving these sums worked, but it was hard work, and there's no obvious pattern to the polynomials. But, obvious or not, there is a pattern, which Jacob Bernoulli discovered about 50 years later. Let's factor out the leading coefficient, then add any missing terms with 0 as their coefficients, and then factor out a certain pattern of binomial coefficients from each term. I'm not going to get into where these moves come from, but look at what this did to the coefficients. Now they're the same in every solution. The first one is always 1. The second one is 1/2. Then 1/6, 0, negative 1/30, and so on. These mysterious numbers are called the Bernoulli numbers, and we represent them with a capital B. The Bernoulli numbers are notoriously baffling, and they show up in some unexpected places. One of their surprise appearances is the value of the zeta function at the negative integers. Well, this was a big surprise for me when I first saw it, but we pretty much just saw exactly where it comes from. When we plug 1 minus n into our zeta formula, we get negative 1 over n times the derivative of the sum of k to the n. And we just saw that this sum is this polynomial whose linear term is the nth Bernoulli number by definition. Well, the way I wrote the polynomial kind of obscures it, but if we just look at the linear term, n plus 1 choose 1 is just n plus 1, and that cancels with the factor of 1 over n plus 1, leaving nothing but the Bernoulli number. And just like that, we've established the formula. Alright, I think that's a good place to end things. If you want to learn more about the topics in this video, there are references to some resources in the description. Anyway, I hope you enjoyed this kind of unusual exploration into the Riemann Zeta function. I'll see you in the next video. Thanks for watching.